Okay. So this is 18.22, and you have a copper bar and where did it go? Yeah, copper and iron. Okay. Okay, so you have two bars, copper and iron, and this is they have the same diameter. D is equal to. I keep losing this thing. Oh, there it is. 2.3 centimeters, and then the length of this, length of copper, is 3.7, and the other one is 0.185, 3.7, 0.37. Okay. Yeah, okay. So what you would do in this case, the current is going through this and comes out the other end. So they're in series. The same current flows through each one, one after the other. They're in sequence with no branching. The current is not like taking off into some other random direction. So the current is the same. So they're in series. You would add the two resistors as if they are in series, not as if it's a fact. So each one out of the copper, this would equal the resistivity length over A. Okay, and then you would be given this. I know it's 1.7 microhm centimeter, but you would be given this resistance. The length is given 0.37. The area would equal a 2 pi r. I mean not a pi r squared. Is the area of a circle. So remember these geometrical things. The area of a circle, it's a circular cross section. It's pi r squared, and this r is given. So therefore, you know the resistance. You can find the resistance of the copper. Do the same thing for the iron, Fe, and this is again going to be rho L over A. Same thing, pi r squared. The length is given. In fact, it's 0.185. The resistivity of iron, I don't know it off the top of my head, but this will be given. And then the radius is given. Somebody's in the waiting room. There you go. Okay. Yeah, welcome. Okay. We are doing problem 18.22. There's a rod of copper welded to a rod of iron. And they give you the dimension. They give you the diameter is the same for both of them. The copper is longer than the iron, 0.37 meters, and this one is a short, 0.185 meters. What's the total resistance? So for each one, you'll find the resistance using the resistivity formula. R is rho L over A. Do it for both of them. They're back to back. They're in series with each other. The same current flows through them. So the resistances add. They're in series. So the same current, the voltages basically add. So the resistances add. And so therefore R total is equal to R of the copper plus R of the iron, Fe, iron. And that's how you do this thing. Okay. Any question? I know I went a little bit quickly. Any questions about any of this? And that's all there is to it. I think our main concern was what do you do about the resistivity? So those will be provided to you. There are millions of materials which have resistivity. Gosh, who keeps going with this? Okay, excuse me for 1 second. Hold on. Hello? Hello? Yeah, my officer, sorry. My team's officer. Okay, thank you. Bye bye. Okay, so back to this, yeah, so that's it. So the resistivities will be good. That's a materials property like density and all those other things. So yeah, you can't be expected to remember such kind of things. Okay. Okay, Maya? Okay. All right, next question. Fire away.
Can you do 19.11?
19.11, yeah.
I just had a question because I didn't know like what angle did you use because I thought you subtract 90 minus 47
Okay.
or if you just use angle 27 given the
Okay.
equation.
Let me. Oh, you can't see it. Is it okay if I hide the paper for a minute here? Okay. What is this thing now? 19. Did you say 1911? Okay.
Yes.
11? Yeah, okay. Is that in the view? No, it's not. Okay. 1911. So everybody read this problem. 1911. Let me read this thing. What do you have here? You have a loop, radius given. Okay. Makes an angle 27 degrees with the uniform. Okay. What is the magnetic flux to the loop? Okay. Given the loop, you're given the radius, angle is given. Okay. 19.11. Okay, I think I've memorized the question, so I can take it off the screen now. Okay, so 19.11. So here, what was it again? Let's see. You have a circle loop of wire, and it's in a magnetic field. So basically, you have this situation. You have a magnet is throwing out a magnetic field, and then you have some kind of a loop which is catching the thing like a fishing net. Now my loop is rectangular, but same idea. In the problem, you have a circle loop. So the more it faces the magnetic field, the more flux it catches. If it's at an off angle, it catches less. That's where the cosine theta comes in. Somebody is waiting to be admitted. Here we go. All right. Okay, come on in, Sandra. Okay, so here's this loop, and there's the magnetic field. And then the angle, so the loop is not exactly, it's not exactly, can you even see this? It's a very thin wire actually. But, the thing is not catching the flux head on, it's at a slight angle. And what is that angle? Makes an angle 27 degrees with the uniform magnetic field. Okay, I hope they know what they're talking about. So 27 degrees. So the area A is represented by a vector which is the normal to the area. So if you have something which has an area, you put a pointy thing on it, that's the vector area. And apparently this angle over here, this is 27 degrees, this one over here. Okay, so that's what you have. So the flux by definition is how big the fishing net is and how strong the fish are, the density of the fish which are coming into the net. So the density of the vector thing that's coming is a magnetic field. Its value is 3.64 10 to the minus 2 Tesla. So this B stuff over here, that's the vector B. And the value of B is 3.64 10 to the minus 2. 10 to the minus 2 Tesla. 3.64 10 to the minus 2 Tesla. So that's the magnetic field. So the flux, the magnetic flux, the B flux, that's equal to the area times the B times the cosine of the theta between A and B. So that's basically it. This A, the only thing to remember is the A over here. This A is pi r squared. It's a circle. And make sure you use the proper unit. And so the R is 4.62 centimeters. So it's equal to 4.62 10 to the minus 2 meters. So make sure you convert the r to meters. So it's 4.62 centimeters. So many meters. Square multiplied by pi, that's your a. That a goes in here. This b is this b, 3.64 10 to the minus 2. And then the theta, if they have worded it correctly, this is where the 27 degrees comes in. So it's not 90 minus that. The 90 is, if properly defined, when they say the area is at 27 degrees, that they should be talking about the normal to the area. So that 90 degrees should already be included in there if their wording is correct. Okay. All right, next.
Can you do 19.44?
Okay, 19.4. So that one was this is worked out in details on the recorded video. This entire problem, and it's like a 2-3 minute long explanation with everything. I'll let you. So anybody else have any other problems?
Can we do 18.57?
18.57. Okay. 18.57. Okay, you can see. 5.7. Where is 5.7? Okay, can you? Okay, there. So 18.57 flashlight with 3 D cell D batteries. 18.57 CL. A 3D batteries, each with the EMF of 1.5 volts. Okay, and then what happens? Let's see, operating the current. Okay, and you have current I. Uh, 0.6 amperes. 0.6 amperes. Yeah. Okay, here. TPD. Okay. So let me take off this thing. Okay. So here's what you have, 18.57. You have 3 cells connected back to back. Do I have any batteries here? No, not right now. But you have the battery cells, and you probably know this. You can have many situations. You connect 1, 2, 3, 4, and so on, one after the other. That's what's happening. So you have these batteries. You have 3 of them connected in series. So the voltages add up. Okay, and now when they are not being stressed, they put out 1.5 volts. But under stress, the more the stress, the less the voltage. There's an internal resistance inside. So the point is for each one, the voltage across the terminal, or TPD, is the terminal potential difference is the same as a terminal voltage, and potential difference is the voltage. So that is 2.8 volts for the three of them, one after the other. So for one at a time, it's going to be 2.8. My goodness, it drops that much. This for the 18.57. Yeah, these are unbelievably horrible batteries. My God, there's a substantial drop actually. So this V terminal, this is equal to 2.8 over 3 for each one. Is this clear? Because you add up the whole. You do your Kirchhoff's rule, right? You start at this corner and you go for a walk. You go up an elevator, you go up another elevator, and up a third elevator. So each time you're going up, up, up. So each one, the height increase or the voltage increase, it's 2.8 over 3. The total height that you climbed is 2.8. So for each of those elevators, you have one sort of this. So this is the V terminal. Now if you look inside a battery, there's an internal resistance R. This whole thing is the cell or battery. Okay, this whole thing is the cell or the battery. So the voltage over here, this is your V terminal or TPD if you like. This thing is the V terminal. This will equal the raw voltage is the EMF. So when this thing is not under stress, this little resistance inside is eating up voltage, because when you go along a resistor along the direction of the current, you're going downstream, so you're losing height. You lose potential in here, but that's only if you have a current. So the internal drop this is equal to I times R. So when there is no current coming out, there is nothing lost internally. It's proportional to I. So this V terminal, this is now equal to the EMF minus I times R. So this is a basic fundamental formula for the terminal potential difference, or V terminal. This is the EMF and minus the internal drop. Is this business clear, how this comes about? Okay, so now this is equal to 2.8 over 3. And what is the question ultimately? What's the internal resistance? Right. And so that's equal to 1.5 minus I was 0.6 times R. So you basically solve for the R. And that's the equation that relates these things together. So I did a little demonstration. I'm measuring two different batteries, and I posted it. It's a short on YouTube, and also part of one of the the video lectures over there. So I thought that was a rubbish battery, but my goodness, this is worse than that actually. That wasn't this bad, and I said bad things about it on the channel. Okay. Okay, next. So
I have a quick question.
Yeah.
During the YouTube video, the first one, I think, you worked out a double dot problem.
Mm-hmm.
Because you worked it out, does that mean we'll have double dot problems on the test, or that was just a more difficult example?
It's a more difficult example. So you won't have a double dot, not that one and not any other on the test. But going through the double dot, it kind of trains you. Single dot problems are like subsets of that. So over there, if you have 3 batteries, the single dot may have 2 batteries, the undotted may have 1 battery, or resistors or something like that. It's a scaled up version of single dot and undotted problem basically. So going through that, it trains you better than doing easier, only easier problems. It's good to see one like hard one done.
Yeah, I was just wondering if double dot was going to be on the exam.
No.
But it's not.
No. Okay, Anna, you're
I
saying?
also have one more question.
Mhm.
Is it just chapter 18 we have 19 we have no dot and single dot? It's chapter 19 just single dot, or either could be like single dot.
No. So no dots on the whole test. No double dots on the whole test from any chapter. So both from chapter 19 and I can never remember. It's 18 and 19. Okay, yeah. So both the problems from 18 and 19, no double dots, dotless or single dot. Okay. But are there any single dot or undotted problems you had difficulty with? There's a small subset of formulas. If you look at the thing, if you understand what's going on, you don't actually have hundreds of different formulas. I mean, when you go along a path, the voltages add up. It doesn't matter whether the loop is closed or not. So it's the same idea. If the current is not branching, you can just add up those voltages. If the current is splitting up, just add the currents at the junction. And there is not much to it actually. Most of it is very, very repetitive. Nothing ultra novel. Just understand the key concepts, the basic physics, the basic science of what's going on. Okay. Ella was about to say something. Or?
I was just wondering if you could do 18.73.
18.73. Let's see. Okay, so let me go back to this. Okay. 18.73. So this, can you see it? No. Okay, there it is. So this, I will say, is sort of beyond the scope of what you'll be tested on. It's not a double dot, but it's a near miss. It's like 1.5 dots or 1.75 dots or something like that. But very briefly, what is the question? Let me. John T. What's the current through each resistor when the switch S is open and when it's closed? Right? So in brief, without solving the whole thing. So I want to do the thing in detail, but just to give you a quick idea. I'm drawing the figure right now. Okay. 100. So let me get rid of this now. So to do this strictly, you'll have to use sort of multiple cases of Kirchhoff's loop rule and junction rule and stuff like that, if you do it formally. Now you can do it kind of intuitively. All of these are the same, aren't they? Yeah, they're all 100. Okay. So, and what's the question here? What's the current through each resistor when switch S is open and when switch when the switch is closed? So these 2 points, A and B, they will be at the same potential, Ella, just from the symmetry. So you can prove that by doing a loop around here, do a loop around there, and you can prove it. But just from the symmetry, I mean, it doesn't matter, you can flip this. This is just a circuit diagram. So these are the same potential. Whether this switch is closed or not makes no difference. Nothing will flow from A to B and vice versa. It's like you have two suspension bridges. There are 2 points in the bridge which are the same height, and you put a cross bridge, so it looks like an H. Do you know what I'm talking about? You have two suspension bridges across a canyon, and then you put a bridge between the two bridges in the middle. If these are the same height and you pour water, it's not going to flow because the height, it's level basically. There's no slope. So whether you connect this or not makes no difference. Nothing will flow across just from the symmetry. So closing the switch or not will not make any difference. And then as far as, what was I asking? What's the current through each resistor? So you can just solve this in a very simple way. So this is gone basically, doesn't matter. So the point is, let's look at this. So from here to here, you have 12 volts. You connected a 12-volt battery there. Go around a loop and you have plus 12, minus 12, then the whole thing is 0. The magnitude of the voltage across is 12 volts. So the magnitude across one of these will be 6 volts. It's going to be half. You can prove it. I mean, this EMF, which is 12 volts, go in this direction. Do a loop like that. You have plus 12, then minus I times R, minus I times R. The whole thing is equal to 0. So each of those voltages you'll solve very easily is 6 volts. So now the current in each is going to be, I will be the Ohm's law, right? That's equal to V over R. And so that's equal to 6 over 100. So that looks like 60 milliamperes to me. So all the 4 resistors will have 60 milliamperes going through them. But this is using symmetry arguments. If you want, one can do the loop and prove what I just said. But just from common sense, these 2 points will be at the same potential. Using the bridge analogy I said with the cross bridge and stuff. But you can do the loops and junction and all that. You'll reach the same conclusion. But overall, this is requiring more thinking than how many dots. It's a single dot problem, which, like I said, it's in between a single dot and a double dot problem. So even though officially it has 1 dot, it's requiring more thinking, more sort of clever thinking than 1 dot should. Okay, but it gives us some good intuition just going through this. No harm. Okay.
Does the same thing apply to 18.71 and 18.7, or would those possibly be on the test?
7.1 is just a straightforward series and parallel combination. And what is the other one you asked? 7.2 again. This circuit here. Let me turn on that. There you go. Yeah. So people know what we are talking about. This thing is called a Wheatstone bridge, by the way. And in more interesting examples of a Wheatstone bridge, the resistors are not all equal. Then there is no point in having a bridge. So usually they're not equal. But so 18.72 again it's a Wheatstone bridge. So we are staying away from Wheatstone bridges.
Sorry, I meant 18.71.
Yeah, 7.1 could be on the test. 7.1 is just a series and parallel, very straightforward series and parallel combination. Remember, we did a similar thing. Yeah, also with capacitors, we did such kind of problems basically. 7.1, yes, but the 2 Wheatstone bridges, which is 18.72 and the other one we just did 7.3. So those are kind of slightly beyond the scope of what can be on this test.
What about 18.70, like the one right above it?
Right above, let me look. Let's see here. Okay, let me move this page here. 18.70, what's the current through the... That could be. That again, that's a very simple circuit. You just have one battery and you have a bunch of resistors. When you have pure resistors, usually quite often you can combine them in series and parallel ways. So this one here, we can do it. Let's see. Let me draw this first. So 18.70. Let me go back to the paper here. Okay, so here's your 18.70, yeah. And these resistors are what? This is 12 volts, so this E is 12 volts. Then you have 5 ohms over here. You have 20 ohms here, 10 ohms. And this is also 5 ohms. Okay. So yeah, this you can have. You can, when possible, and what is it asking for? What's the current through the 10 ohm resistor, which is the 10 ohm? Oh, is that it? Okay. That would be 0 actually. Okay. So that's one thing. And what else? Oh, and the 20 ohm resistor, this one here. Okay, so these are the two parts of the question. You have a bunch of resistors thrown together, like a bowl of spaghetti. They're connecting in all kinds of interesting ways. And this is the battery, the big plate here, that's positive, and this is negative. So the current will go like this and go around, and eventually it's going to come back. So now over here, notice that you have a wire going across the two ends of the 10 ohm resistor. So anytime you put a wire across, the wire is a 0 resistor. So it's like the 10 ohm is in parallel with a 0 resistance. Is this making sense? Eli, was this your question?
Yes.
Yeah, okay.
That makes sense.
Yeah, so here.
Can you repeat that, please?
Yeah, so let's look at this thing over here. So it's like you have a 10 ohm, and then you have a 0 ohm. When you have a wire, it's a 0 ohm resistor. So you have a 0 in parallel with a 10, which makes the whole thing become 0. 1 over 0 is infinity, right? So 1 over 10 plus 1 over 0 is infinity. 1 over infinity is 0. So when you parallel 10, and if you parallel anything with 0, the answer is 0. Because 1 over something plus 1 over 0 is infinity, and 1 over infinity is 0. So when you do the reciprocals and all that, this is a wire. It has no resistance. Or if it's a good one, it doesn't have any resistance. So this thing is 0. So as to the question, so this thing over here is a 0. So now that the circuit changes to, it becomes the following. So, so as far as the first question is concerned, what's the current through the 10 ohm? There is no voltage across the 10 ohms. This is what's called a short circuit, by the way. This is the reason houses burn down and stuff like that. If accidentally you touch these two wires together, the current has a short circuit. It has a short path, zero resistance path, and therefore it basically bypasses this whole thing. So there is no current, so this will be zero. There is no voltage across that. And now this circuit looks like this. So let's redraw this, putting a zero here. Remember we did an example in class, and maybe it's on the YouTube video also. I did a circuit. You successively condense the circuit. There were two resistors at the right end of the circuit. I even remember that. They were in parallel, so you combine them. Now the circuit simplifies to just one resistor. So you simplify things, step by step. So now this is looking like this. Okay. Something like this. It has become this. So this is 5, this is 20, this is 5, and this whole thing is 0. Okay. Now does anything...
Explain again how you need to look at that specific portion to
How-
find the
How it went from here to here?
10 ohm resistor?
From here to here?
No, just the top part, like the first part you did.
Oh, here?
Yeah.
So
How
here...
do you know to look at that portion specifically for that?
Oh, so look at some of the previous solution with that more complicated circuit. Step by step, if you notice that something is in series or parallel, go ahead and combine them just to reduce the number of variables. Is that making sense? Sandra, do you have video?
Were you looking at? Oh yes.
Okay.
Were you looking at like the wire as a parallel resistor in that case?
Yeah, so this wire, so in fact, so you know, here it is. This is the one we did in class, I think. Yeah, so you'll know what I'm talking about. Just a minute. Let me refer back to this because we've done this one. Come on. Okay. Where is it now? Okay, we did this in class, and I believe it's also on the YouTube video. Remember this problem? The top figure, left figure, figure 18.52. Do you remember the first thing I did? I noticed that the two 56s are in parallel. So I combined them, and 1 over 56 plus 1 over 56 and 1 over the whole thing. That made a single resistance of 28 ohms. So the you can't see my face. So the first thing I did is I collapsed the two 56s into a single 28 ohms. Do you remember this? But even if you don't, that's what you should always do. And try to look for things which are series and parallel, and combine them, so you have the circuit becomes less complicated basically. So so that's exactly what I'm following the same process over here. So here I noticed that this you cannot combine this with this. Why? They're not in parallel. Parallel means both ends should be connected together, right? So they're not. The top ends are connected, but the bottom ends are not directly connected. There's something in the way. So the 10 and the 20 are not in parallel. So don't bother with those. The 5 is not in. It's not in parallel with anything. It's also not in series with any of the resistors, because it's not in series with the 20. Why? Because the current is splitting up. Series means end to end. So the best catch we have right now is to notice there's a wire going from there to there across the 10 ohm. A wire is a resistor. It's just whose value is 0. So I notice the 10 is in parallel with something. So I go ahead and that's why this big pink bubble I have there. I collapse these like this. I have a 10 in parallel with a 0. right? And if you just do the parallel calculation, you will get a 0 for the answer. So that lets me put this whole thing I can replace with a 0. And that's what I did over here. This is a 0 ohms. It's a wire. Is this making sense, Sandra? Okay. Is everybody else okay with this so far? Okay. Now, the next thing to notice, and by the way, what was the question? And never sort of, always have your eye on the prize. What it is that we're actually, what number was this? 8.70. 8.70. What is it asking? Oh, yeah, the current in the 20 ohm resistor. So what is the I over here? Okay, so back to this. So now, as I mentioned, anytime you notice something is in series and parallel, go ahead and combine them. The next thing we notice is, ask the question, is 5 in series with 20? Is it in series with 5? No. Is it in parallel with anything? No. So forget about the 5 for now. But 20 is in parallel with 5. Do you notice this? 20 is in parallel with 5. Why? These ends are connected, those ends are connected. That's just a wire. It's like twisting them together, twisting the ends together. I used to have resistors here. They're gone now. But both ends are twisted together. Is this clear that these two are in parallel? Parallel doesn't mean they should be parallel in a geometrical sense. They seem like they're at a, it's more like a triangle than a parallelogram. Doesn't matter. They are in parallel because these two ends are connected together. These two ends are connected together. So everybody make sure you fully understand and appreciate this point. They are in parallel. Make sure you're okay with this.
Would that also be equal to 0 then?
No. These are connected together. What that means is I can redraw it like this. The 0 is not in parallel with either of them. The 0, this is not connected across 20. It's not connected across 5. It's connected across the two ends of something. It's not shorting out the 20 and this 5 ohm resistor.
I'm only a little confused because I don't understand how the 20 resistor and the 5 resistor are in parallel if there's a wire in between them.
There's always a wire. These are wires. See, even here, when you say something is in parallel with the other, you always have a wire. It is the wires that are touching each other.
So why wouldn't the 5 resistor and the 20 resistor be in series? Like the 5 resistor closest to the battery.
This one, but question is in series with what?
In series with the 20 resistor.
It's not because the current is splitting up. For them to be in series, a series means one after the other. You cannot have a branch. If you have a branch, the current coming from here is splitting up. So to use the series formula, the series formula works because the current is the same in all of them. Therefore, you can add the voltages. But here, the current, some of it goes through 20, some of it takes a long route. It goes through 5. You don't have the same current in 20 and 5. Okay, so the current is different in these. So it's not in series. You have branching here. The current goes around like this, but then it's splitting up. The whole current doesn't go. Some of it goes around through the 5. Some goes to 20. So they are not in series. Okay, so think deeply about this. Make sure you fully understand what's happening over here.
I have a question.
Yeah.
So if the 0 resistor wire had resistance, would 20 and 5 still be in parallel?
Oh, so instead of a 0, if you had, like, for example, 3 ohms over here.
Yeah.
Like this? No. Then the 20 and 5 will not be in parallel. For them to be in parallel, for series, you should have the same current. For parallel, you have the same voltage. That only means both ends should be connected together. You see, so but if you have a 3 ohms here, the voltage across the 5 is not the same as the voltage across 20, because the voltage now, previously the problem was the current was getting split up. Now the voltage gets split up. The term uses divided. It's the same thing. The voltage gets divided.
Okay, thank you.
Okay, sure. However, to make it interesting, let's say you do have a 3 ohm. What can you do now? You can't parallel the 20 and the 5. This 5 is like, hopeless. It should basically, go jump off a bridge. There is no future for that 5 right now. But among these 3 here, suppose you have a 3 ohm there. You cannot parallel any of these. Okay. Is there something you can do? You have a 3 here.
Could you put the 5 and the 3 in series?
Exactly, yeah. You can put the 5 and the 3 in series. So if you have a 3 over here, you can put the 5 and the 3 in series. So this thing over here, like this. Okay, I think I refer to these things as sausages when I did a similar thing in class. It's a bent sausage, but it's a sausage nevertheless. So you can add them. So this whole thing now becomes 8 ohms. Now the 8 ohms is in parallel with the 20. So now you can use your parallel formula. Not for 20 and 5, not for 20 and 3, but you can use it for 20 and 8, which is the series combination of 3 and 5. Okay, this is slowly starting to make sense. It takes a while to kind of get used to this idea. So you cannot put this sausage in parallel with 20, the 8 ohm thing over here. Okay, but back to the original question when you had a 0 over here. If you have a 0 here, then you can think of it this way. When you had a 0 here, the 0 is in series with 5, which makes it 5. Now that 5, the new sausage, which is just 5, it's in parallel with the 20. So no matter, you can parallel the 5 with the 20 when this is 0. Okay. Is this providing some clarity, or is it adding to your mental confusion? Hopefully it's okay. Yeah. So now proceeding with the question. So now you have 5, not 8. You just have 5. So if you like, you can think that the wire is in series with the 5. Wire has 0 resistance, so 0 plus 5 is 5. This whole thing is 5. This 5 is actually in parallel. Both ends of the sausage touch the 2 ends of the 20 ohms. And so now you parallel the 5 and 20. So now you have 5 in parallel with 20. This is equal to a 1 over the 5 plus 1 over 20 and 1 over the whole thing. Is this clear? Okay. And so what is that equal to? That's going to be 4 plus 5. How much is this? Isn't that 4? I think it's 4. You check. I put a question mark. I did it quickly in my head. I think that's 4. So now you have a new circuit which is even simpler. You see how we are simplifying the circuit in a step-by-step, combining things, series, parallel, and so on. So now you have this battery like this, and you have the 5, and you have a 4. Okay, is this clear? So it has been reduced to this circuit, that original one that you had. We are now down to this. Now you can find, and we are assuming the battery has no internal resistance. There's no mention of internal resistance. It's a very high quality battery. So it's not, the voltage is not getting eaten up inside the battery. So was this 12 volts? It is 12 volts, yes. So now the voltage across 5 and 4 is equal to 12 volt. So you can now do a Kirchhoff's loop rule, going around like this. So loop like that. That's my loop. So you have plus 12. So I'm starting over here. Start from the left lower corner. It seems like a logical place to start. So you go up, you take an elevator, you go up by 12, then you're going downstream, and then you come back to take the ski lift one more time. So now we have a minus 5 times I, minus 4 times I. This thing is 0. And so therefore I will equal, what will be 12 over 9. So this is 1.33 amperes. So that's the current. This,
So if you can't add them in series or parallel, should you just turn to the Kirchhoff's rule and see if you could do that instead?
you can. Yeah, absolutely you can. Yeah.
Like, should that be your next step if you can't find any more series and parallel?
Correct. So the series and parallel, the derivation for series and parallel, which you won't have, but that came from Kirchhoff's rule in the first place. So that's like a special, like a simple application of Kirchhoff, where so you end up with a 1.33 here, and now you can get the voltage across this. So V across the 4 ohms is equal to 4 times I, and that's equal to 4 times 1.33. So in volt. So this is the voltage across 4 ohm. And now back to the original question. Where is the original question? What's the current through the 20 ohm resistor? So this is the voltage across the 20 ohms. So if you look over here, the 20 is in parallel with 5. That's why you ended up with the 4 ohms. See? Using the parallel formula of 5 and 20 in parallel is 1 over 5 plus 1 over 20 plus 1 over and so on. So you have 4 ohms is the combination of 20 and 5. The voltage across the 20 and the 5 is the same. That is the voltage across the 4. That's just a combination of those. So the current in the 20 using Ohm's law, so I in the 20 ohms is equal to a V in the 20 ohms divided by I in the divided by R, 20 ohms. Well, it is 20 ohms, and so that is equal to now for this number here, 4 times 1.33 over 20. So this is the answer to part B. The answer to part A is 0. There is no current in that the 10 ohm resistor. So this is the current in the 20 ohm resistor. This seems longer than it actually is because I was explaining it and we had a lot of discussion and questions and things like that. It's not if you kind of were to just do it, just look for parallel, series, combine, and in the end use Kirchhoff's loop rule or junction rule. Everything will follow very straightforwardly. Okay, is this clear? This was a good example to do, by the way. Okay. And
I know we're probably like out of time, but
mhm.
I just wanted to know how in depth we needed to be like aware of the hood of conductors and insulators for in like the theory. This is like when I was reading through the notes, it talked about like look under the hood of conductors and insulators.
Oh no, forget about that.
And also the same with the P-type and N-type
Yeah,
electrode?
no, skip that. Skip that.
Okay.
We didn't
And
go.
then
We didn't go
my
into that.
last question is for the photodiode when it's going off. When the switch closes for a second, is that what conducts is that what powers the conductor? And then when the light's on, it shifts
Let me bring it up. Let's see.
I just wanted to make sure my understanding is
Yeah,
correct.
let me bring up that document here. Mm.
Like when the switch closes, the battery,
Yeah, I understand. Right.
like the voltage goes through the switch and charges the capacitor, and then when the light goes off,
Yeah,
it charges the diode. And that's how the photo's taken?
yeah, hold on. Let me bring it up so we have this figure in front of us. Where is this thing? Where the heck did it go? Okay. I thought I had this up here.
It's in the lecture note 3 and also in lecture note 4.
Mm-hmm. It's not open, that's why. Okay, I think we can open it now. Where is it now? Oh man, okay. Okay, but yeah, I'll just redraw this. So I think I gave you the simplest version, which is okay. So here, so how does this thing work? This is a semiconducting device. Okay, so it's a device that's a semiconductor, and if when light is not, it's on the borderline between an insulator and a conductor, so it needs a little bit of a push to get those electrons moving and to get the thing conducting. And that push comes from the light. So initially, when before you take the picture, you know the camera, everything's in the dark, the shutter is closed and all that stuff. You close the switch. This is done by the camera electronically. You close that switch, so then this battery, this is negative positive, it gets connected. This end is already connected to the capacitor and the diode. But when you close the switch, this negative gets connected there. So the capacitor gets charged negatively and positively like this. Now, as long as no light is shining, and then you disconnect it. So you have, suppose this is 5 volts. You have 5 volts sitting over here. It's like you fill a tank of water, and then assuming it doesn't evaporate, it kind of just stays at that level. But now you make a hole in the tank, or you open a faucet. So the longer you keep the faucet open, and the more you open it, the more degree to which you open it, water is going to flow out. So by looking at how much the water level dropped, you know exactly how long the person spent in the shower or whatever it is. So you know how to build that person basically for the water. So same thing happens when light is falling on here. This is light. Okay. Light falls on here. It gets the diode conducting. So the more intense the light, the more conductive it is. The longer the light is shining on the thing, the more the charge leaks away. So it's like opening the faucet to a different degree and a different duration. So that's what the diode is doing. So you lose charge just the way you lose the water in the tank. And now you have a circuit comes and checks like how many what percent of the charge went away. So from that it knows it makes that pixel that dark or that bright accordingly. The computer knows when it shows it on your screen what should be the brightness. And you do this for each of the colors separately, red, green, and blue. And then by combining...
Eventually, like, will the semiconductor use all of the voltage from the capacitor, and that's when you have to recharge the battery?
No, the battery, we are assuming the battery stays charged.
Okay.
The battery stays charged. The capacitor doesn't have its own chemical reaction. It only has the charge that you put on it. It can't generate more charge. It's a passive device. So as a result, once you put some charge there, you just measure how much of it leaked.
So the main idea that we need to focus on is that when the light is shined on the semiconductor diode, it takes some of the voltage from the capacitor.
No, the language should be it conducts, not that it takes a charge from the diode. It starts to conduct when light is shining on it.
Okay.
And so because it conducts, it's like having a resistor here. This is going to basically leak out its charge through the resistor. It becomes a resistor. Before it is a resistor, but it's infinite. The R is infinite. So the rate of flow is zero basically. But as you shine more and more light, the R drops. And I did a demo. I don't have this with me right now. But I think...
yeah, I remember the demo. I just want it to be like 100% on.
Right. And what you're thinking of, I don't know why this thing is not popping up on the screen over here. But the thing you're talking about later in the same notes, I have a slightly more advanced description of this business. And that's coming after the summary of the chapter, if you look on the review. And I've graded out. It's in a faint gray. So that's material which will not be on the test. The thing which is in faint gray. But after that you have these pictures of these voltmeters, and I discussed this in class yesterday. How you should connect a voltmeter. Whether its resistance should be high, low, ammeter. It's a pity this thing. I think I opened. I started this video software before I opened this document. So for some reason, it doesn't see it anymore. But yeah, that's basically what the story is. So the meters and all that, they will be. So just look at the review that I've posted. The things which are in gray, you can skip those sections here. Teaching. Okay, does it make sense? What happened if I add this?
So we shouldn't go off like the lecture notes like 3 and 4. We should just look at the test review notes.
Yeah, the test review is very similar to the class notes. But then I cut out a few things here and there. And also both chapters are together. So you have one document instead of two. So it makes it in a slightly more compact basically.
Sounds good. Thank you.
Okay, sure. Okay, so everybody's feeling okay and someone better about the test for tomorrow?
I have just one question.
Okay.
For us taking the exam with the SDRC, will we have calculators, or should we just leave stuff before putting in the calculator?
You can leave it, or they might provide you with some simple calculation. You can ask them if they'll provide you, but if they don't, you can just you can put a note there that they did not provide you with the calculator, and you can just leave it unevaluated, like you did last time. Okay. Okay, so everybody's ready for tomorrow? Okay. So I'll see you guys, most of you, tomorrow in the class, and then hopefully I'll have them graded before Monday. That's the plan. Okay.
I actually have one more question. When we have epsilon and the electric motive, like symbol, they both kind of look the same. Will it be like deciphered? Which one's the electric motive symbol? Which one's epsilon?
Oh, so you won't encounter the epsilon in these chapters.
Okay.
The epsilon basically it temporarily died with chapter 18. Okay, it may re-emerge, re-emerge in a future chapter, but for now it's on vacation. Yeah.
Even if it's used in chapter 18.
Yeah. So the script E, that's the battery voltage, the electromotive force, when the battery is open. Okay.
Thank you.
Sure. Okay. So see you guys tomorrow then.
Thank you.
Okay. You're welcome. Okay. Bye bye.
Thank you.
Yeah. See you. Bye.
Thank you.